Hello everyone. Today I am going to prove the mean and variance of gamma distribution. Mean of the gamma distribution is defined as integration of the function f(x) multiplied by the variable to the given range a to b of the random variable x. After substituting the value of probability density function f(x) in this bracket, we have 1 by beta to the power alpha gamma alpha integration from 0 to infinity e to the power minus x by beta x to the power alpha dx. Here, if we integrate this function integration by using integration by part, we lead to the improper term for the range infinity. So we have to use the gamma function as let this term x to the power x divided by beta is equal to t. We have derivative of dx is equal to beta times dt when the range of x is equal to 0, t tends to 0, and when x is equal to infinity, t is equal to infinity. Then we have the expected value of x is equal to 1 by this constant term multiplied by e to the power minus t. After substituting the value of x is equal to beta t power alpha, and the value of dx is equal to beta times dt. Then after simple calculation, taking the constant beta to the power alpha plus 1 outside the integration, the denominator term remains the same and it becomes 0 to infinity e to the power minus t to the power alpha dt. To apply the gamma integration, we make this power alpha as alpha plus 1 minus 1 to evaluate the integration by using gamma function as 0 to infinity t to the power n minus 1 e to the power minus tt is equal to gamma n. Here the constant n is equal to alpha plus 1. So by using this integration, we obtain the gamma of alpha plus 1 of this integration. Then we have the mean of the this distribution is equal to alpha times beta. Since the gamma integration alpha plus 1 is equal to alpha times gamma alpha, this gamma alpha is cancelled out, and thus the mean of the gamma distribution is equal to alpha times beta. Similarly, to calculate the variance of this distribution, now the variance of gamma distribution is defined as variance of x is equal to the expected value of x square minus square of the expected value. So the value of ex square is equal to integration of x square fx dx minus the value of expectation is alpha beta to the square. After substituting the value of this probability density function in the first expression, we obtain this term 1 divided by beta to the power alpha gamma alpha, which are the constant out of the integration, and the integration is e to the power minus x by beta x to the power alpha plus 1 dx. This x square and x to the power alpha 1 minus 1 is simplifies as x plus 1. As earlier, the integration of this term by using the by part lead to the improper term for the upper range infinity. So we have to use gamma function for this. Let x by beta is equal to 2 as in the mean. This implies derivative of x which is equal to beta dt. When x is equal to 0, t tends to 0, and when x is equal to infinity, t tends to infinity. And this gives, after substituting the value of x to the integration, we had this constant term outside the integration e to the power minus t. Substituting the value of x is equal to beta t to the power alpha 1 plus 1, and this term is the derivative of x dx is equal to beta times dt. On simplification, and after taking the constant term out of the integration, the integration become e to the power minus t to the power alpha plus 1 2 minus 1. This t to the power alpha plus 1, this alpha plus 1 is breakdown to the t to the power some positive number minus 1. To apply the this integration of the gamma function, we obtain the gamma function of alpha plus 2, and the other constant are simplified as beta square divided by gamma alpha. And the gamma alpha plus 2 is breakdown is after break down this gamma function into the term alpha plus 1, alpha and gamma alpha, and this gamma alpha and gamma alpha is cancelled out, and the remaining part is summarized as taking beta square is common, alpha time alpha plus 1 minus the alpha square and alpha square is cancelled out, and the variance is alpha beta square. The variance of gamma distribution is equal to alpha times beta square. Alternatively, if the probability density function of gamma distribution is defined in the following form as the parameter alpha and lambda, in this form, the probability density function is defined in this term as lambda to the power alpha e to the power minus alpha times x and x to the power lambda minus 1 divided by gamma lambda, then we can easily prove the mean and variance of this distribution as lambda by alpha and lambda by alpha square. Mean as lambda by alpha and variance is lambda by alpha square.